Hello, in this set of videos, I'm going to prepare you to start wiring and programming your microcontroller. We'll start by talking a little bit about safety, and then we'll go into the different components that we have for this first week of assembly, and we'll revisit some of the requirements that we had from our first class period. We'll then talk about wiring diagrams, and before you're allowed to power any of your systems, you're going to have to show your wiring to other groups in the classroom. And then we'll go about programming our microcontrollers, and specifically we're going to use a new programming language, relatively new programming language called TOIT. In the end, this is what we'll be building up to. This is the complete wiring diagram for this first week. It allows us to control both motors, run off of a battery, and drive the motors from this motor driver connected through all these wires to our microcontroller. But before we get there, it's important for us to do a little bit of background, a little bit of basic circuit theory, so that you sort of know the intuition behind why we have some of our safety protocol for the class. So I'm going to start with a fairly imperfect analogy, but this is pretty commonly given to first-year electrical engineering students, and it'll take you a long way as long as you don't take it too seriously. But often we think about voltage as water pressure. So if I'm going to draw a diagram here, maybe we have something like this. We have a hill, and at the top of the hill we have some sort of pipe. And that pipe goes down the hill and outflows at the bottom. So how high up the pipe starts compared to where it ends is related to the pressure. So you can think of raising this up as increasing the voltage and increasing the pressure, which means our current will be higher. And you can think of current as the amount of flow. If it helps, you can even imagine your electrons as being what actually is flowing through the circuit. On the other hand, electrons, in the case of this analogy, I probably shouldn't even mention it, would be sort of flowing uphill. I just don't want to have you thinking that electrons actually flow in the direction that current flows, which will come up later in this set of lecture slides. And finally, on this chart on the left, we have resistance. And resistance is like a flow limiter. So you can imagine something, having something in the pipe right here, and that would be a resistor. And it's going to limit the amount of electron or water flow through the system. This is called Ohm's law, the relationship between these three quantities. It's called Ohm's law. And the little circle on the left is supposed to help you remember the equations for all three of them. So V is equal to I times R. And you're supposed to remember that by saying that V is here, and the relationship between I and R is that they're right next to each other, like multiplication. And if you wanted to do some algebra, you could see that I is equal to V over R. Just like you can see I is equal to V over R. And then it probably goes without saying, but we can also compute our last quantity here, which would be V over I. One last physical unit that we'll talk about is power. And that's just I times V, so the current times the voltage. So if you've ever heard about your charging brick being a 45-watt charger or a 109-watt charger, that's related to both quantities, the current times the voltage. So throughout this set of slides, you'll see me write diagrams that look something like this. and maybe some extra components that I haven't mentioned yet that look like that. This for now is just a made-up diagram that has no real meaning here, but I just want to fill in some of this diagram early here so you have some of these symbols in mind. So this here on the far left is the symbol that we typically use for something like a power source. In this case, our power source is going to be a battery or the USB cable on your computer. This here is the symbol for a resistor. And you might see that have a quantity, something like, I don't know, 330 ohms. When you have a resistor and voltage, that means the voltage is going to be pushing current through the resistor, assuming the circuit is actually closed. So you'll have a current, and we usually indicate the current as going from the positive sign, wrapping around back to the negative sign. That's the flow of current. It's actually the opposite flow of electrons, but that's the flow of current. This last symbol over here, as computer scientists, you should have some comfort with. That is a transistor. And it behaves a little bit like a resistor and a little bit like a switch. So a lot of times if you see a circuit with a transistor, we'll just draw that same circuit in a couple of different ways. Once with the switch open, and once with the switch closed. One other thing I forgot to mention is this symbol over here in the bottom left. And that's just a symbol for ground, meaning the lower potential energy side of the battery. It's not technically necessary in a simple circuit like this, but it's a habit that I've long since had. So for this diagram, our microcontroller would be controlling this switch. That's essentially what a transistor is. It's an electrically controlled switch. And when the switch is open, there's actually no current. I would be 0 in this case. There's actually no current flowing through the resistor or through the switch. There's no connection here. There's no way for us to continue the loop. So no current flows. On this one though, we would have a current. And we would be able to calculate it based on the voltage here, the value of our resistor here, and it would be simply I is equal to whatever that voltage is divided by whatever that resistor is. So if I went a step further over here and said that V is equal to, let's say, 5 volts, we would be able to compute I is equal to 330, sorry, not 330, 5 over 330. And that would give us the amount of current flowing through that circuit. That brief little tutorial on circuit theory is really just so I can use some of that terminology when talking about our safety requirements and talking about the specifications of the components that we'll actually be using this week. So I'll start with this warning on battery safety. So lithium-ion batteries may explode or burn due to improper use. So if you drop them and you notice them bulging or some damage to them, make sure you let me know. If your battery smells odd or is hot, those are also things you should let me know. Lithium-ion batteries are fairly safe, and I bought extra safe batteries, something with protection circuit built in. But it's very worth knowing that you should treat them with some respect. All right, so there's a lot more information listed on the course website, which is why I just have this called the Selected Battery Safety Tips. You should definitely read what's on the course website. But I don't ever want you to discharge the batteries below 3.2 volts, and I will only ever charge them about to 4.2 volts. If you're going to store the batteries for any period of time, you really want to do that at about 60% their capacity, something like 3.5 to 3.7 volts. Batteries are a little bit confusing in these numbers because the lithium-ion batteries are actually 3.6 volt batteries, sometimes 3.7 volt batteries. But we charge them over that, and they can actually be discharged to below that. So it's just sort of the nominal rating for them. Likewise, I have just some selected electronic safety practices. You should definitely read the entire set of tips on the course website. But some of these are sort of self-explanatory. Always check for loose wires and debris whenever you're powering on your circuit. Going back to these diagrams, what you don't want to have had happened is a wire to accidentally be bridging this gap. Let's say there's just a random wire on your circuit, and it's bridging that gap. Well, that's going to close your circuit when you thought it was open, and even worse, there's actually nothing dropping the load here. So, looking at our equation, that means resistance is close to zero, and so your current is going to be as close to infinite as the battery is going to allow it, which is going to get very hot, and it's going to, it's going to burn and potentially explode. So definitely always check for loose wires and debris before powering your circuit. Always disconnect before adding any new connections. Always have an eye on your battery's voltage level. I'll describe how you can do that throughout this set of lecture videos. And keep an eye on the heat. So you can usually smell heat. You should also test your components every once in a while by putting your fingers close but not actually touching them. You don't want to get burned. And be careful with static electricity. You can actually fry your components by dragging your feet around the carpet on a dry day and building up a lot of static electricity. Alright, so I'll reiterate one last time here. The important part is for you to read the entire list of safety tips on the course website.